Hello, my name is James Maura. I'm an electrical engineer with Group 4, also known as Bright Descent, and we are doing the Gravity Light project, and I am in charge of the control system user interface subsystem. For my subsystem, it focuses on monitoring the electrical performance of the gravity light and displays information to the user in real time. The system tracks information like voltage, current, the power usage, the estimated battery level, the charging status, and the projected LED runtime. The main hardware I worked with includes the Arduino Nano R4, an OLED display, and multiple INA 219 current sensors that communicate over I2C. Within the overall system, my subsystem acts as a link between the power electronics and the user interface. The sensors collect the electrical data from different parts of the system, the Arduino processes that information, and the OLED display provides live feedback to the user. Okay, and here's a code for testing the OLED display. And first we start by initializing the libraries that come from the Arduino. The wire H library essentially enables I2C communication between the Arduino and the OLED. And we also have the UAG2 library, which initializes the display and also where the characters go. First, we initialize the OLED driver, and then we clear the buffer. And this code right here essentially outputs when the OLED gets power, it's going to output a simple statement, which is gravity light, and OLED is working to give us the information that the OLED is working. And in the end, it just the send buffer just sends that information to the OLED to be displayed. And here we can see that the OLED is working fine and is able to display the information from the code that we gave it. To allow for multiple of the current sensors to operate on the same I2C communication line, each sensor needed its own unique I2C address. And by default, all of the INA 219 sensors use the address of 0x40. And so this conflict would occur if multiple sensors were connected without modification. And so to solve this, all we did was just solder bridges between the A0 and the A1 address pads on the sensors, which allowed us to change the address to different addresses for each of the sensors that we had. This was a code that we used to verify that each device was being detected correctly on the I2C bus. And all the program does is initializes the OLED display and checks for communication with the OLED itself and each of the current sensors using the address that we assigned each one. And here we have the check device function, and all that does is it sends a transmission request to a specific I2C address and checks whether the device responds successfully. And when the device responds successfully, we display that information on the OLED. And as you can see here, the check device function is working, and so there's communication between the OLED and all the three sensors, and each one of their address is displayed right across right here. And with this, we'll be able to test the current in 3 different parts of our system. To ensure the capability of each current sensor, we connected the current sensor to the load of a 4 kilo ohm resistor attached to a 5-volt battery pack. And we used the Arduino to send a signal to the OLED to output the power, the voltage, and the current readings. In this test setup, all 3 of the current sensors were connected to separate load resistors while sharing the same I2C communication lines with the Arduino. The OLED display was then used to show live current readings from all 3 sensors simultaneously in real time. This demonstrates that the sensors could successfully operate together on the same system while providing continuous electrical monitoring. As development continues, the subsystem will also expand to estimate the battery percentage, the charging time, and remaining LED runtime for the final gravity light prototype. Purpose of this test was to verify that a 3.7 volt battery could successfully power the Arduino Nano R4 and OLED display using the 5 volt buck boost converter. Since the Arduino requires a stable 5-volt input, the converter was used to step the battery voltage up to a stable operating voltage for the control subsystem. And in this demonstration, a 3.7-volt battery is connected to the 5-volt buck booster converter, which powers the Arduino Nano R4 and OLED display. A simple test program was uploaded to confirm that the system was operating correctly under the regulated 5-volt output. Once powered, the OLED display the message "Power OK" and Arduino ready, confirming that the converter was successfully supplying stable power to the subsystem. And in conclusion, the control subsystem successfully demonstrated real-time system monitoring, sensor integration, and battery-powered operation for the Gravity Light project. Through testing with the Arduino Nano R4, OLED display, current sensors, and the power regulation buck booster, the subsystem showed that it can reliably monitor and display important electrical information needed for the Gravity Light final prototype.